Discovery intelligence is a scientific decision support system. It requires profound internal logic to structure claims, experiment requests, and belief updates into a coherent lattice. It is common to assume that machine learning models act as the core decision makers inside a platform like this, but models have a strict limitation. They output raw pattern signals and probabilities. They do not possess the capacity for explicit, step-by-step reasoning. To make those probabilities useful, the system requires a deterministic logic layer positioned above the models. Something has to interpret the raw signals and decide what actions they warrant. Inside Discovery Intelligence, Python functions as this interpretative layer. It acts as the primary system for reasoning and coordination, executing the logic that translates raw data into scientific meaning. Machine learning outputs provide the pattern, but Python provides the framework that defines what those patterns represent within the scientific process. Python acts as the primary reasoning and coordination layer of the entire system. It houses the scientific reasoning rules, manages the workflow coordination, and executes the state transitions that govern product behavior. Python acts as a vertical integration lattice, reaching down to bare metal silicon operations to trigger memory allocation and CPU branching. By spanning these tiers, explicit scientific rules translate directly into machine-level control flow. A complex rule becomes a simple condition check. To see how this reasoning is executed in practice, we can track a single piece of data as it moves through this architecture. Python transforms abstract scientific methodology into executable behavior. It serves as the bridge where high-level decision rules become specific CPU operations. A scientist begins a session by uploading a raw dataset into the system. Python first engages as the system's integration glue layer, receiving the upload request through the Fast API framework. This diagram displays the dynamic inward routing. Python splits the workflow, sending the data along separate paths to specialized tools. Along these paths, Python calls third-party integrations like RDKit to featureize molecules and invokes scikit-learn models to generate predictions. Python orchestrates this entire sequence using fundamental control flow mechanics. It checks conditions, loads values into memory, and executes branching logic based on the incoming data type. This initial ingestion phase converts unstructured tabular data into the specific formats required for scientific workflow coordination. The process data now moves into the system's service modules, specifically the claim service, where the explicit reasoning lives. Python operates as an object-building layer. Raw data flows into empty slots within a crystalline wireframe, creating scientific objects. It maps numerical predictions into this form, instantiating a claim object. This deterministically generates a linked experiment request object bound together by explicit Python rules. In generic web development, service modules route data between an interface and a database. In this system, the service modules contain explicit scientific reasoning that dictates how evidence is interpreted. Without Python structuring this object hierarchy, the system would possess only disjointed predictions. Building these objects creates testable, working hypotheses. A new data payload enters the system, the empirical experiment result. At its deepest operational level, Discovery Intelligence functions as an intricate state machine. This microscopic view illustrates the collision point. The new experiment result is evaluated by binary gates against a static numerical threshold. Python executes an explicit transition rule. If the numerical result is above the threshold and the quality is good, the underlying support is strengthened. The inverse is also strictly governed. If mixed evidence exists or the context is weak, the rules dictate that the system's posture is weakened. The physical manifestation of this logic occurs in memory as the claim object morphs into a new state, recorded as a belief update. This specific moment is where scientific reasoning is executed as a mechanical transition from one bounded state to another. The deterministic nature of Python state transitions guarantees that the system's scientific evolution remains justifiable and inspectable, rather than hidden inside an algorithmic black box. The newly formed belief update object moves downward, out of temporary runtime memory. Python serves as the bridge between temporary scientific thought and durable scientific memory, writing structured state through SQL alchemy into PostgreSQL. As shown in this diagram, Python rolls up multiple historical and current updates, interlocking them to rebuild the canonical belief state. This massive foundational grid of belief state ultimately dictates the product behavior that the user interacts with. Python controls specific UI outcomes, how session comparisons are built, how support quality is surfaced, and exactly how actionability is phrased. The intuitive decision picture presented to the user is the final visual rendering of Python's underlying deterministic memory states. This wide-angle landscape maps the complete causal journey as a single continuous pipeline. Python routed the upload, built the claim, interpreted the result, transitioned the state, and rendered the decision. If Python were removed from this architecture, the workflow coordination, state transitions, and object construction would collapse entirely. Machine learning models provide the pattern signal, but Python explicitly decides what that pattern means inside the system. This fly-through represents the bare metal reality. At the lowest practical level, this intelligence is simply CPU instructions executing explicit control flow. Python is not magic. It is the essential explicit language of thought, coordination, and state transition that makes discovery intelligence possible.